quick question. How many of the people here in the room have held a 3D printed part in their hands? Oh, pretty good number. So that's good to know. And then how many of you have actually seen a 3D printer in action? Pretty good number. So we got a lot of the engineers stuck around. So I'm going to talk about a kind of narrow slice of 3D printing. 3D printing is a pretty broad technology, and it's part of rapid prototyping, which I'll cover also sort of more generally. And I've been working with engineered parts and medical device development for 20 odd years, and my first 3D printed part was in 1994, so it's changed a lot in that time, and it's continuing to evolve. And I know, those of you that know 3D printing, it's changing quickly, and it's really hard to keep track of things. But I'm going to talk a little bit about some of the specific uses and the specific ways that we've put 3D printing to work in our shop in Novartis. So first I'm going to cover prototypes more generally. How do we think about prototypes, and what are prototypes good for? I'll go a little bit more deeply into a few of the processes, and then get into a little bit of the practice of how we actually put this to work in medical device development, particularly for our inhalers. So focusing on prototypes. So prototype, it's that first thing you make, and it's really the first things you make. There's many prototypes that come to life in the process of getting a medical device out the door. Put this one in for John. You'll probably recognize this as an early prototype of the Exuber inhaler, which eventually became this guy. So this is a little bit further along. It's not the super early prototype. John's shaking his head. But this is what we need to get to from something that we can hold in our hands that's been made one-off. This guy here is machined parts and probably some 3D printed elements as well, painted, and this is a commercially available, or was commercially available device. So the way we get there is these iterative cycles. We take an idea or a vision, and we go through this design, build, test cycle, and end up with a working prototype. And actually there's several cycles in between. There might be a series of subsystems that we're iterating that we then blend together and different other subsystems, and eventually we end up with something that we think is going to work. And in Novartis, we have a bit of a taxonomy of the prototypes that we use, and each of them has a bit of a different function, a different target. And so we might start with a proof of concept breadboard, and it's really focusing on function. Can we get the aerosol that we want? We then might move to what we call a semantic model, and we say semantic in that, what is this device communicating to the user? Does it have the communication that we intend, which is really in the human factor side? And then an architecture model. We then kind of go into CAD, and this is where we're really trying to fit it all together. Can we get it more or less in the size that we want? Can we get the function we want? We haven't really touched into the human factors again. We're kind of inside out as opposed to outside in. And then we've got an appearance model, which might happen in parallel, which is more outside in. We kind of settled on the size, and we know what we want it to look like. But this appearance model is fixed. You can't turn it. It doesn't do anything. There's no aerosol coming out of there for sure. But then we move into a handling model. Now we're getting things fit together. It's kind of faked in. We may have the twist mechanism. In this case, this is the Simoon inhaler that we developed actually as a second generation product for Exubera back in the day. And this has the right size, has the right appearance, it's got the right human factors, and we can start learning about how patients will interact with it and start improving our product as a result. We then move into an investigational prototype, and here you see the first appearance really of our 3D printing. This is a stereolithography model with a variety of different parts, but here are the actual components being put together. Now I don't really care about what this looks like. I want to make sure it works, it's the right size, has the right features. And then we move into a functional appearance prototype. This is using quick turn injection molding, where we're actually making parts that have the real materials, that have the features, and it's starting to actually look like the real deal. In our pilot scale device, we're adding robustness. Now we have something that we think can last long enough, certainly for maybe an early clinical trial, but what we really want is our early clinical device, where we really beef up the appearance and the robustness. And this is just a sample of 9 different prototypes that got us from here to there. There's many more that didn't make the cut in terms of the picture. So talking a little bit about processes. There's a lot of processes out there to use, and we've selected a narrow number of them that we put to work in our labs or with our external vendors. So one of the challenges we face when deciding which process to use is this balance of throughput and speed. Throughput and speed versus resolution or precision, and that will drive the process choice. So early on, we really care about throughput. We want to get these iterations. We want to move fast and break things, as they say at Facebook. We want to fail fast to learn faster. And therefore, a process that supports that is really important, and high throughput is important, but resolution may not be as crucial. Later in development, resolution is starting to be more crucial as we need to get something that can actually work, that can actually deliver the product. So, talking a little bit about these processes, I'm going to cover 3 different classes of processes: subtractive, net shape, and additive. And with subtractive, you start with a block and you cut chunks away, and each of these processes, each of those cuts takes time and takes effort, and ships fly and you're leaving material behind. And if you want to make something like this, you can imagine it takes a lot longer to cut through all that material to get this crazy web shape. So simple subtractive mechanism is laser cutting. It's very fast. It can be really appropriate for things that are two-dimensional. It's fairly low cost to have one of these in-house, and quick to learn. It's inexpensive to operate. Has a lot of benefits, but it's only for flat shapes. So I can cut 2D shapes and stack them together. I can create 3D shapes by stacking 2D shapes together. Materials are somewhat limited. We can't cut steel with this. And the edges, they're going to be burned. They're going to be melted. It's hot laser cutting through your material. Benchtop CNC milling is a lot more advanced here. This is computer numeric control of a series of mill tools. This replaces having a machinist in the shop. We can get our engineers to learn how to do this, but there's a bit of a learning curve. It takes some training to operate. It can be kind of messy, but it's pretty fast. We have a very wide selection of materials that we can use, and the fidelity of the shapes that we get out is really high. So this has a place as well. Now moving into net shape prototyping, this is conventionally net shape has really been focused on production, molding, and casting and other types of forms of net shape apply here as well. But we've started working with net shape because it has some real value. So we first start with building a tool. So this is the negative of a form that I might fill. I'm then going to add plastic. Now I've molded my positive to get rid of the tool. The screw disappears, and now I've got the shape that I want. That's how we get there. Now, if I want something this complicated, obviously I need to build that into the tool. Taking the time to build that tool is substantial. So the more complicated the tool, the longer time it's going to take to build, the more it's going to cost. So quick turn injection molding is a process that we've used to make real parts. And this is tooling that isn't commercial class, but gets us really high fidelity, really good accuracy, and we can mold those parts in the materials that we intend to use, which has extreme benefits when we get to inhalers and the surface characteristics of how our aerosol engine might interact with the aerosols that we're putting through it, and powders. We have a wide selection of materials, which is great, but it can take 2 to 3 weeks to get a quick turn mold. Back when I started as an engineer, getting molds under 12 or 16 weeks was unheard of, and now we're getting them fast and cheap. But relative to these other rapid prototyping processes, it's fairly slow. It definitely requires the investment in building a tool, but then you get a bunch of parts that you can build hundreds, 200s, but if you're trying to build 5 parts, it's really not the best choice. Printed injection mold tooling is a similar process, but you're using 3D printing, which I'll discuss a little bit more in a moment, to actually make the inserts for your mold. And this is, again, good. You've got a wide selection of materials, and it's definitely less expensive than quick turn injection molding, but there are a lot of limitations in terms of what you can do, in terms of the shapes that you can manufacture, and the tool life isn't very long, so you're not going to get a lot of parts out of these guys. So 3D printing, it's additive in nature. So we basically build the shape that we want from the beginning. That complexity is essentially free, which frees up designers. If they spend the time to design something intricate and complicated, building it may take actually less time than it would with other processes. So you end up with things like this. The picture on your right is a bespoke innovation sparing, and I give credit to Scott Summit, the founder of that company, for this complexity is free concept, and it really frees up people to come up with the craziest thing they can think of. And as we get towards the point where 3D printing becomes more reliable and cheaper and more sustainable as a commercial manufacturing process, you'll start seeing parts that you wouldn't be able to see otherwise. Now, how do we get to a 3D part? Well, we start with a CAD model, computer-aided design, and then press a button, and you get your STL, your standard tessellation language file. It creates a bunch of different triangles, and this is used to define the shape to the instruments or the machines that are building our 3D printers. A simple one is called fused deposition modeling. It's fairly coarse, but it's fast, it's cheap, and it's really easy. So we've got a couple of these in our shop. Basically what you have is a filament. This head here is blown up here. So you have this filament of build material and a filament of support material, and I'll explain that in a moment, that come through a heated head and are extruded out. So it's a thick piece of thick wire of plastic that is extruded into very thin wire and layered on top, and the heated plastic fuses to itself. And what you see here is support material, right? So this shape here is floating off in space. I need to build some support material to hold it up so that when it ends up there, it's not going to droop as I build it. So the support material is essential. So this is what 3D printers look like these days. These are a couple in our shop. These are Dimension U prints. You see the MakerBot replicator has been it's sort of brought 3D printing to the masses. It's a couple $1,000, it might be $4,000. You can get these for your home now. They do have some limitations, and you're not going to make the sweetest parts, but they really have changed the way we design, because we can build things and run them in a few hours and have parts in our hand. It's really refreshing and really changes the way we think about the way we interact with our designs. So here's an example of a fused deposition modeler building something that should be familiar to all of you. Mm-hmm. And you started with the support material, and now it's coming and actually laying down the ABS plastic. And it's fairly robust, and this, like you said, like you see there, it's about 60x speed. Building, this took 25 minutes. It's not particularly big. I've got one in black here. So there you go. Builds that in 25 minutes, and we're ready to go. Now, obviously not the most practical usage of it, but it gives you a sense of how this might work. Stereolithography is another very common form of 3D printing. So stereolithography apparatus, or SLA, it's not a service level agreement, it's a stereolithography. It gives much finer detail, but these are big machines and they're fairly complicated to run, and there's a process of removing those supports which requires a little bit more effort than with FDM. With FDM, we can just throw it into a chemical bath and they dissolve and we're good to go. With SLA, they're physically removed and have to be kind of hand fettled to get down to the right point at the end. But it's fast, it's high fidelity, and this is really important again when we get to aerosols, because the nature of FDM versus SLA is that SLA has a much better surface characteristic and air tightness relative to fused deposition modeling, which will give us air holes and things like that may impact your aerosol results. So we've got a good range of materials, which is nice, but like I said, it's big, and you've got the kind of the latest, greatest from 3D Systems, and then this is a hobbyist one called the Form 1. They're becoming available faster and cheaper, but I would say, caveat emptor with home SLA machines, they're definitely messy, and they definitely take some hand-holding and fine touch to make sure they work right. So here's an SLA part being built. Now in this case, it's 1000x speed, so this took a while. It's a fairly big part. So one of the things you'll see here is that these supports are being built in the middle. This is a cap for the breeze-hailer device. And those supports need to be removed, and there you can see that they're the same material. It's not a separate material in the case of as is in the case of FDM, where the material characteristics allow you to break them apart more easily. Because it's the same material, you actually have to physically remove them, and they try to get them down to a fine point, but it still leaves some stuff behind. So the finishing And the post-processing of these parts is really important to get something right. So we've kind of gone back to the same vendors over and over to make sure that we get that right. And as an example of 3D printing exploding, I found this productchart.com that shows all the 3D printers that are available at, I would say, at the sort of consumer or prosumer level. And I've already narrowed these down, as you can see, to assemble and software included. So if you want to build your own 3D printer, that one's not even on here. And this is a huge range if you're going price to print volume. So it's exploding in the industry. And now this is one that just came out recently, it was announced in March, that is even faster than any of these others. It basically uses SLA with some optimization to speed up the time between layers, which is really the rate limiting step with SLA. And so I haven't had a chance yet to build a part with this. I'm looking forward to it. The company's about 10 minutes away from our office in San Carlos, located in Redwood City. But rest assured, I'll be building parts with this one and seeing if I can get a capital request. So, covered prototypes and processes, now practice. This is where the rubber meets the road and how we use it in our shop. So we've thought about it in the sense of through concept to device, as maturity of the design increases, we look at different processes in different ways. And we've also divided it between prototypes and the fixtures, the prototypes being really the inhaler itself. And the fixtures. So the fixtures, we might use a laser cutter pretty much for both prototypes and fixtures, but it's going to have a much longer life in fixtures because the 2D shapes may actually play a bigger role as we move on. Fused deposition modeling, again, it's better suited for early stage prototyping, whereas the FDM, which we keep in-house, is going to give us good bang for the buck long into our fixture development. Stereolithography we don't really use for fixtures. It's not really appropriate. It doesn't really give us the kind of price and time trade-off for what we need with our fixtures. It's not really there, but for prototypes of our actual devices, it's very helpful. The benchtop mill comes into play later on when we're making more robust fixtures, so this might be things for release. And the injection molding tool. Again, this is something we're going to shop out, but using quick turn injection molding or insert or printed molding is going to be something that's going to happen later on in life as the design moves to the point where we have that need for precision and throughput becomes less of an import. So here's some example of some laser cut parts. This is a flow cell that was built, assembled, the whole thing in less than an hour. So getting from the idea of I've designed it, I've built it, I'm testing it really quickly. Laser cutting can get you there a lot faster if you're willing to do this buildup of materials and you're willing to take some of the trade-offs in terms of not having 3D contours. It's also great for making bezels and stuff for our in-house instruments, and for less practical applications, it has some nice benefits as well. Benchtop CNC mill. This will allow us, for instance, to build a variety of gears really accurately with the ability to vary the bore and get the right fit and get that developed to the point where we know what we want to tool. So there's some real advantages to having the CNC in-house. As you can see, it does get a little messy. The chips fly, and I keep telling engineers to clean up, but that's the way they leave it. And then fused deposition modeling. So in-house, really helpful for a lot of assembly and test fixtures. One of the big advantages is we can make parts that we wouldn't be able to make really with any other process. For instance, this one you see was this undercut here that allows us to just snap in this instrument here. We wouldn't really be able to make that any other way. We also get the flanges for free, and so we get this level of complexity that's great, but the trade-off is this surface finish, right? We can accept that for a fixture that's not going to work for a device. Stereolithography, on the other hand, gives us really fine detail, and we can use a range of materials, and we can, by keeping this as an external supply, we can get a variety of materials in the same order, bring it all back, because they've got multiple machines running, each one running a different material, get those back at the same time. And some of that is mechanical properties, some of that is going to be simply the color, so we can tell which part is which. And you can see that we can also print in the specifics of the part and then just use Sharpie to have it come out in relief. So that allows us to track very easily which part this is, because we can assemble it and there's no question, because it's built right into the model. As an example of comparing FDM and SLA, I took a small part, this guy's this big, this small cutter part, tiny little part, and an SLA and an FDM. Now, I would never, I know better than to make this out of FDM, but we went ahead and did it just for kicks to show the difference, and you can see this fine detail where we've got a cutter edge, much finer detail on SLA, whereas this is the best the FDM machine could do. Then SLA, we can enhance these parts. The SLA is great, but the material tends to be fairly brittle, and it also tends to be fairly sticky. So two things we can do. We can add inserts, brass inserts, so we build the model with a bore large enough to pot in and glue in a brass insert here, and then use mechanical pencil with graphite to reduce the friction. So this is a simple way of making the parts actually serve the purpose a lot better. And then the last thing I wanted to show in terms of our practice of how we use rapid prototyping at Novartis in San Carlos is quick turn injection molding. So this is something that wasn't really even conceivable to me years ago as a young engineer getting our tools built. Two separate tools, $2,000 each, 35 millimeter height here, by the way. Part cost 70 cents plus $300 setup. We can actually prototype using injection molds, and we can test out the materials and get those right material properties in the shape that we want so much faster than we could before, that it really allows us to speed the development of our devices and make them much more effective, because what we get in the end, we know is going to be reliable. And with all of these, there are slightly different shrinkage rates of these materials at the size that we're molding. We thought that was going to be negligible. So with that, I want to acknowledge a few of my co-conspirators, George Axford, Mark Glusker, and Glenn White, who are the guys really in the shop, the makers and designers making this stuff really happen. And thank you all.
Thanks, David. Amazing. Okay, will the three speakers please come up?